Hi there, and welcome to this lesson on predicting entropy changes. In the last lesson, we looked at calculating entropy changes with numerical values. We learnt that during a chemical reaction, we've got both the system and the surroundings at play, and they both undergo entropy changes. And we need to use both of those values in order to work out the total entropy change. Because total entropy change takes into account our enthalpy changes, temperature, kinetics, and everything. And then we applied that to whether a reaction was feasible or not. So we learnt that a feasible reaction needs to have a positive total entropy change value. So in this lesson, we're going to learn how to predict those without the numbers, and then we'll have a look at some equations, and we'll try and infer from the information we're given whether we think the overall entropy change is going to be positive or negative. So remember, entropy, as a definition, is defined as the randomness or the disorder of a system, or of the energy of a system. So the more dispersed a system is, the higher or the more positive the value of entropy is. So we can see in our image here, there's a greater value of entropy on the right-hand side. In a reaction, an entropy change takes place as the reactants are changed to their products. Before we carry out any calculations to work out the total entropy change, we can actually infer a lot just looking at the reactants and the products and comparing them. Things we can compare. The first, most obvious one is the number of gaseous molecules increases as we go from the reactants to the products. Because remember, the arrangement of the particles is more random in gases than in solids and liquids. The second thing we can look for is the overall number of particles increases as we go from the reactants to the products. Generally, in a reaction, when the number of moles of products formed is greater than the number of moles of reactants, then the entropy value is going to be positive. Conversely, if we look at it in the other direction, we're going to get a negative value for our entropy if the number of gaseous molecules decreases or if the overall number of particles decreases. Let's have a look at some examples. So looking at this equation here, predict whether we would see a positive or negative entropy change. It is a positive entropy change. That is because we've got a greater number of gaseous molecules on the product side. Well, we have none on the reactants, we've got 1 mole on the product side. And this example here, the entropy change is negative because we've got less gaseous molecules on the product side than we do on the reactants. So the overall entropy change, or the overall entropy, has reduced. And this example here. So everything's in a gaseous state here. So now really what I'm looking at is the overall number of molecules. So we can see the number of molecules on the reactant side. There are less molecules. There are 2 moles versus 4 on the reactant side. So overall, the entropy change is negative. And finally, this one. There is a decrease in the overall number of molecules when we look or when we compare the reactant side, so 2, and the product side, 1. Therefore, the overall entropy change is negative.